This chapter 6, what we'll do is move forward with and more specifically link up the basic mechanistic science to the speed and power reserve models and how they work quantitatively to both explain performance, but also to allow users to be able to predict performance. So chapter 6 will be relatively short. I'm going to introduce the quantitative basics of the model. It's pretty simple. We'll step through it without too much detail, but enough detail so that you can understand what's there and provide linkage between the scientific concepts and the relatively brief math that's needed to express and use the models. So performance prediction is where we'll end this chapter. We had looked earlier at the determinants of endurance performance, and they're relevant again for this chapter. So what you see on this slide shows three variables: VO2 max, or maximum aerobic power, running economy, and the percentage of VO2 max. So individual measures of VO2 max and running economy on an athlete, really any endurance athlete, and the knowledge that I showed you of the existing knowledge provided by databases on the fraction of VO2 max that's utilized for events of different durations, whether it's 5 kilometers, 10 kilometers, or marathon. The existing knowledge of percentage of max plus the individual measurements on athletes allow for quite precise performance predictions of what that athlete can do. And in an earlier slide, I showed you Jack Daniels, Mick Saltine, and Dave Kostal. Kostal is pictured here on the left. He's the middle individual in that old black and white photo. The person in the foreground there is Bill Rogers, who's a 4-time champ of the Boston Marathon. And we have a contemporary East African runner on the right. I believe it's Wilson Kipsang in a modern marathon. So this is worth revisiting because the linkage between measurements on individuals and their performance capabilities was one of the goals that Dr. Bundle and Matt Bundle, had when we started this. And as we move forward, I'll show you the math that enables you to do that in the sprint intensities. So for the endurance zone, this is similar to the slide I showed earlier. We can do individual measurements, and with existing knowledge, if we know the velocity, VO2 max, running velocity, VO2 max of an individual, which is a combination of running economy and VO2 max, those two things combined, we can predict quite well for different durations what the speed that athlete can maintain will be. So when we started the speed reserve and what became also the speed power model, or excuse me, the speed reserve and the power reserve model at the Concord Field Station, the first thing that we did, this was the very first set of experiments, is that because we were interested in explaining sprint intensities in relation to duration and what the basis of that was, and ultimately hoped to be able to predict it, the first thing we did was to recruit athletes that were highly specialized that would have different curves. So we recruited sprinters, middle distance runners, and long distance runners to maximize the differences in essentially the shapes of those curves of the sprint versus duration, or the performance versus duration curves. So recognizing, in this case, for example, for the long distance runners, we intentionally recruited high-level long distance runners that had no running speed, that couldn't sprint, because we wanted really flat curves to be as different as possible from the curves of the sprinters, who would be very fast at the short end and come down rapidly and not fast on the longer end. And the middle distance runners, of course, would be somewhere in between. So we wanted to maximize differences by recruiting specialized athletes. And so in these athletes that we brought in, and this was again at the Concord Field Station, we measured their top sprint speed. We just kept increasing the treadmill belt speed over a series of discontinuous bouts until they failed to get down, and we would go to an 8-step failure with full recovery in between. When we got to a speed where they could not get down 8 steps without coming backward on the belt, we measured a couple times. We knew we had their top speed. We measured their maximum aerobic speed. We did discontinuous test up to VO2 max, so we would know at a series of speeds what their rates of O2 uptake or running economy was. And once that curve was in place, if we had the maximum, we just put the max on the curve, and we used that method to quantify the velocity of VO2 max. And And then we took all the athletes from the 3 different groups and we put them on the treadmill for roughly 15 bouts apiece at different speeds with full recovery, some fast speeds, some slow speeds that we knew would wear them out, they would hit their failure point at different durations. So for example, we would set the treadmill at speeds that we expected to, they would only be able to sustain for 10 seconds or 20 seconds. We would do this at a series of, constant speeds that were different to essentially populate an entire performance duration curve for each athlete. Each of them was instructed to stay on the treadmill as long as they could at every one of those velocities until they couldn't keep up with the belt. So we took those 3 steps, top speed, speed of VO2 max, and then an entire speed duration curve of 15 different velocities and durations that they could maintain to have an individual curve for each one of them. This will give you an example of what these tests look like. This was later in Texas when we did these performance duration measurements. In this case, this is on one of the double amputees that we tested, Oscar Pistorius. In progress, that's what the tests look like. So we would do 15 tests like this, where we would set the belt at a constant speed. The athlete, whether it was in the initial case, it was not amputee athletes, but intact limb athletes. They would get on the belt and they would go as long as they could before and we had a criteria. They had to, if they slid back behind a certain point for more than 3 seconds, we would terminate the test. We would give them a warning. They got back up, they'd keep going, but once they slid behind for 3 seconds, we would terminate the test. And that's what they look like in real time, so we do 15 of those to get a performance. So this is what that original data set looked like. So you can see here that the curves for the sprinters and the triangles starts up high, and if we move out on the duration end on the x-axis, you see at the far right, the lowest point, the slowest point for the longer duration is the sprinters. On the shortest end, the sprinters are the highest, of course. If you look at the open squares, those are the distance runners that we recruited, and as I mentioned, we got high-level distance runners that could not sprint. We intentionally got those guys, the classic marathoning types that don't have a sprint gear. They can run at a high velocity, high steady velocity, relatively high, all day long, but they can't notch it up very much. So you can see how flat their line was. So we succeeded with those athletes, and the middle distance athletes fell in between. Out on the long end, our mid-distance athletes were probably slightly higher caliber. So at the far end of the right here, the open circles, they were actually faster, and these were not these running durations were not that long. So you would expect at a duration of 100 seconds or 150 seconds, the mid-distance athletes would in fact be faster than the endurance athletes, and that is what we measured. So what you see here, this is where I'm breaking the data down just step by step, transforming it simply to in the manner that we do for the speed reserve model. So what the top graph shows, and I mentioned we had speed duration curves for each athlete, but we also measured their top speed and their speed at VO2 max or their max aerobic speed. So what you see on the top panel are the same 3 groups of athletes: the sprinters, the mid-distance runners, and the long-distance runners, with their speeds that they were able to run at different durations, and the durations are on the x-axis. And in this case, on the top panel, those speeds are plotted on a relative basis. So 0 on the y-axis of the top panel represents the speed at VO2 max, and the everything above that is just the absolute speed. So if the speed at VO2 max was 5 meters a second and they ran their trial at 7.5 meters per second, that would correspond to a speed on this panel of 2.5, et cetera, et cetera. So we just subtracted off for every trial their velocity at VO2 max, and what you see are these nice curves. As you would expect, the sprinters have the highest velocities because they sprinted quick, they ran quickly, and their VO2 maxes were lower. The mid-distance runners are in the middle, and the long-distance runners are at the bottom. So On the bottom panel, what we did was we expressed their top sprinting speed as 1 and their velocity at VO2 max or their maximum aerobic speed as a 0. And when we did that, the curves of all three groups collapsed into a common curve. So that bottom panel shows the speeds that they ran for their speed duration trials, roughly 15 apiece, expressed in relative terms with the lower boundary being their velocity at VO2 max and the upper boundary of 1 being their top speed. And that standardization collapsed all the curves. So that's a very significant result, because what it shows is that on a relative basis, that runners move as the duration of sprinting becomes longer, how much speed a runner loses is the same fraction of that difference between their top speed and their top aerobic speed, or their top sprint speed and their max aerobic speed. And that difference is the speed reserve as it's defined in the model. So we have one curve for everybody. This is a different view of it to make it a little bit simpler and a little bit more schematic. If we come back to performance as a function of duration, and we include both sprint and endurance durations for a wide range of durations on this x-axis, what the result that I just showed you said that if athletes are operating at intensities above their aerobic maximum, which of course would be the minimum place you would identify a sprint, or possibly, depending on your terminology, a middle distance event. But anything shorter than say 7, 8, 9 minutes, which would correspond potentially 10 minutes or 11 for a well-trained athlete, that would correspond to that maximum aerobic intensity, or here for runners a running speed, max velocity at VO2 max. As we move up into that higher exercise intensity zone, that the performances of athletes are very predictable function of two inputs, their max sprinting speed and their max aerobic speed, and that on a relative basis, when expressed relative to those two speeds, there's one curve for everybody. So everybody conforms to that same curve. And again, this is the basis of the speed reserve model. So if we do this for individuals that have different capabilities for speed as a function of duration, what you're seeing again on the x-axis is run duration. On the top panel, we have individual curves from two athletes, one a sprinter, one a distance runner, as labeled. The distance runner subject 7, the sprinter subject 1. So you can see, and we have these open circles are all-out treadmill runs that I just described, where they were run at a constant speed until they couldn't keep up with the belt at a series of differing constant speeds, and therefore the slower speeds they ran longer, the faster speeds they ran shorter, to obtain a speed duration curve for each runner. So for the sprinter, as you would expect, on the short end, the speeds are quite fast, and the speeds come down. If we express them as absolute speeds, they come down more rapidly than they do for the endurance runner. So that's subject 1 is the sprinter. Top panel for subject 7, that those short end velocities are at around 8 meters per second. The individual is not super fast, and the line is a lot flatter. So as we get out to these longer durations of 200 seconds and above, the distance runner's curve is above that of the sprinters. But if we do the normalization or standardization to the speed reserve model, where we assign the speed at VO2 max or max aerobic speed a value of 0, the top speed a value of 1, the curves of these two runners superimpose, as you can see on the bottom panel. And the open circles here are trials that we administered on the treadmill. The closed circles are trials that we administered on a 200-meter indoor track. We used the indoor track at Harvard at this time. This was our second data set that we collected, and we conducted the track trials of 1, 2, 3, and 400 meters with flying starts to simulate the treadmill, so we wouldn't have an acceleration confound between the constant speed runs on the treadmill and the trials that we did on the track. We did fly-ins of 30 meters or more, so they could be up to constant speed. And you can see this is just a simple with two athlete example of the treatment of the data using the speed reserve model, showing in the case of these two athletes that they conform to the same relationship in the bottom panel, which is part of that model. So one way to think about this is that everybody falls on that same curve when it's expressed relatively. And so there's a common clock. Essentially, we can describe this curve with an exponent. I'll show you that coming up. And that curve, again, is, when expressed in relative terms, is the same for everyone. So you can think of it as a common clock. And to give you a simple example, for runners, that time at which runners hit the halfway point between their top speed, the top red line here, and their maximum aerobic speed, the bottom red line, that time turns out to be almost 60 seconds on the button where they hit the halfway point in between. So that's one way to conceptualize this common clock. So here it is with actual data for an individual, and the math, which I'll step you through. It's relatively simple, and it's not difficult. And we've done enough so far with these concepts that I think at this point it should be understandable. So our speed max here is max sprinting speed. Our speed air is the max aerobic speed. And for this individual, we've got all the curves. And we've plotted the line given by the equation here on the bottom for the speed reserve. And the speed reserve is defined here at the top. It's the top speed or top sprint speed minus the top aerobic speed. That is your speed reserve entity. If we do the entire equation to go from, and what we're doing now is doing the sprint equivalent of where we started with the endurance athletes. We can measure running economy, measure VO2 max, and for any duration or any length event, we know what fraction they're going to run at. We can predict how fast they're going to run quite well. So, but here we're doing it for sprinting, and this is the secret sauce for sprinting, which is the speed reserve model. The full equation is here at the top. The speed at any time, t, is a function of the aerobic speed, that speed air, which is essentially a baseline. They're not going to run any slower than the aerobic speed in the sprinting intensity zone. And what you see on the right is the entity in parentheses is the speed reserve. It's the speed maximum, max sprint speed minus the aerobic speed. And then what comes out to the right is a natural log, and it's elevated. It's expressed to an exponent that has a negative value to make the curve come down. That's the k. The k is what just sets the bend in that curve. The higher k goes, the sharper the bend. And then t is the time of the duration of the sprint. So if we have a measured aerobic speed and a sprint speed for any time in that sprint zone from 2 seconds out to 180 or even longer seconds, we can predict exactly how fast that person is going to run. So if we break it up, we've got on the bottom here, you see the speed air is the sustainable portion, the baseline portion, and everything that's non-sustainable above it is quantitatively described in terms of the speed reserve model by the difference between the max sprint speed and the max aerobic speed with that time expression that says how quickly those things come down. From how quickly, as a function of event duration, the all-out running speeds of the athlete will decrease from the upper limit down toward the lower one. So these are original experiments that were done at Harvard by Matt Bundle and myself with the athletes that I've shown you. We originally did this in 2 different data sets. So both of the data sets are plotted here. The results from the athletes expressed in terms of the model. So the equation that I just showed you, we have a measured speed on the treadmill and a predicted speed, both on the treadmill and on the track, here for 24 subjects, both of those data sets. 366 runs, you can see that the predictions of the model, the speed reserve model, which is just the equation I just showed you based on 2 measurements, top speed, top aerobic speed, plug and chug, and for predicting their all-out speeds for durations from a couple of seconds out to as long as here, roughly 5-6 minutes. You can see that their performances are dead on what the predictions are. So in one sense, the ability to quantify and predict, there is linkage between that and kind of the mechanistic considerations that we started with metabolics and mechanics. And the next steps as we move forward will be to tie those things together. So it's one thing to have an equation that predicts, but the equation also has meaning in terms of interpreting those scientific concepts that we've laid out, going through back to the beginning chapters. So one note of interest that helps to bring these things home is when we were testing Oscar Pistorius. This was back in 2008, when there was a fairly intense controversy about his blades and whether or not he was advantaged by them. One of the things that we did with him, which turned out to be important in terms of evaluating that question, was we did a speed duration curve. We thought that it might be important. We were also interested in seeing if there was a lot of speculation that the prosthetic limbs, that the blades were enabling him to be more fatigue resistant than the other runners. And so we knew that time course as efforts extended longer and longer. We knew the time course, the relationship between that and how much runners should slow down. And as part of our testing of Pistorius, we measured his top speed, which was critical. We also measured his aerobic speed, and we did a speed duration curve. And this was subsequently done at Colorado Boulder for Blake Leeper. And of course, the interesting question was, scientifically, did the blades alter that relationship, or did these athletes conform to it? And in the end, they conformed. So this is from the CU Boulder researchers, Alina Grabowski, Owen Beck, Paulo Taboga. The speed reserve model, the absolute velocities as a function of running time on or duration on the treadmill is on the x-axis on the left, and the velocities that were measured is on the y. So the green diamonds are Oscar Pistorius. The data collected by the CU Boulder researchers, this is from their paper, is the orange diamonds, those are Blake Leeper. The other three athletes in Pistorius, those were all measured in Texas by us and plotted here in their manuscript. What's important is moving from the absolute speeds on the left to the speed reserve expression, or the relative speeds on the right, where the zero velocity is max aerobic speed, the 1 is the max sprint speed, and what you see is for the open circles, which are the three intact limb athletes, and the diamonds, orange and green, which are the two bilateral amputees, that everybody falls on that same line. So the answer to the question of, did the blades somehow provide sprinting endurance capabilities to these bilateral amputees, was clearly no. As the duration of an all-out run got longer and longer, their decrements in speed or performance were predicted exactly by the speed duration, by the speed reserve model, and how it predicts those speed duration relationships will occur. And so the scientific outcome from that's important is that the blades were not conferring any sprinting endurance advantage, and this test showed that fairly conclusively. It did leave open the question, and there was still a fair bit of confusion about this, and I'll hit it only briefly, because it's only indirectly related to the speed reserve considerations that we're undertaking here. But the reason that the pacing of their 400-meter races was different than those of the intact limb runners. They would start slower and finish faster. So that led to speculation that they had greater speed endurance that was conferred by the blades. But this result said, during constant speed running, if you take the acceleration part of a race out, and the bilateral amputees simply were not able to accelerate as quickly, which provided them with fatigue-sparing effect at the end, their anomalous pacing was not due to greater speed endurance. It was due to the mechanical effects of the blades impairing but not fatiguing their ability to accelerate at the start, which then enhanced their ability to come home at the end. And that was one of the more subtle scientific messages, that it was hard to get people that didn't know and understand this model to recognize, which was a very clear and solid conclusion from our data. And I've included this because it's a nice example of the kinds of things that the model allows you to do. in terms of performance prediction. In this case, with the Pistorius controversy, because he conformed to this relationship, we were able to take his top speed and based on our projections of how much it differed due to the blades, we could translate that directly into how much time he would save over 400 meters, and it was substantial. And we did the same thing subsequently with Blake Leeper as a function of his limb length. So, so the long and short of those examples and the math that I've taken you through to link back to the concepts that we originally covered is that since that curve is the same, all you have to do is measure top speed and top aerobic speed on anybody, and you've got there. You can predict in that anywhere in that intensity zone above the max aerobic speed, you can predict what they're capable of doing for a few seconds out to 5 minutes, 10 minutes, and anywhere in between, pretty much. But the other nice thing that fell out of this, because that curve is the same, every curve populates every point, every data point for an all-out run from a few seconds out to many minutes falls on that line. So you can also work it the other way, where you don't have to go through a laboratory test to measure the maximum aerobic speed, which takes some time and trouble. The top sprint speed, not so much, but and that can be easily done on the track. But mathematically, what it meant was that we could take, because the curve had the same shape, we could get points on the curve and work out to the inputs that we originally used, which would make applying the model a lot easier. So here's an example of that. So again, we have this expressed in the terms of the speed reserve model. There's the run duration on the X, the speed on the Y. And here we've got, in red, we have 2 points on the curve. And if we know the shape of that curve, essentially it's just like knowing the equation for a line. If you know the equation for a line, you can plug in any X and get a Y. So the math is slightly less straightforward, but it's essentially the same process. If we have any 2 points in this line, we can and we know the curve, we can populate any other point on this curve algebraically. So, and that's it. That's why am I telling you that? Because it simplifies the application of the model. It means you don't have to go into a lab and measure the top aerobic speed. You can measure in your athletes what's available to you. If you have a 200-meter run and a 400-meter performance, if those are both valid data points where the athlete didn't have a bad day or sprained their ankle, if those are representative of their measures of their performance capability, that's enough for you to do this entire curve. So in practice, what a lot of the track and field community began to do was measure a fly-in 10-meter speed, which is a relatively easy, low exertion thing to do. You just set up timing gates, you give them a wind-in of 30+ meters, and then you get a blink to get their top speed. And then if you have a longer run, you can either administer it, like a 300-meter run or a 200-meter run, or you could just get it from their races if they happen to race those distances, and then you had the entire curve for that athlete. So we've got highly accurate predictions that are possible from the scientific work and the original data that we acquired for two purposes, really. One was the hard thinking about what the mechanistic basis of performance was, and I've taken you through a lot of that logic. But an equally important goal was being able to apply it so we could put it in the hands of coaches and athletes to make performance predictions. And what has happened initially, what happened was something we didn't expect. We were very focused on basis of performance, but initially a number of the coaches recognized, well, particularly Ken Jakowski recognized, oh, I can use this for training prescriptions. If I want my sprint athletes or mid-distance athletes to run 150 meters at 92% of their maximum, I know with this algorithm what their maximum is. So although we didn't specifically anticipate it, this was applied for performance prediction purposes, training prescriptive purposes fairly readily, which we thought was a nice application that fell out of it. And it only requires those 2 points, as I noted. It's highly accurate. And one of the things that was done early on by Ken Jakowski was to line up athletes in different places. He could time stagger them for all-out runs and magically get them to come in at the end based on the algorithm. So that does it for Chapter 6. We'll pick up and advance a little bit further to link up prediction with mechanistic understanding in Chapter 7.